happy New Year of all your new friends, so that's awesome. How was lunch? Sort of good. Tired? Still good? You have your caffeine? Yes? Okay. All right. So, what I want to talk about this afternoon is expand. I'll time better. Dina told me to push really hard on this marker, so we'll see if I do better. Talk about the courage. I have no more to do. So Valeria did already a really great job motivating why we want this. And I will mostly talk about one side of this triangle, essentially the relationship between logic and programs. Okay, so we're going to only look at the relationship between propositions and types and proofs that will correspond to programs. So, in particular, okay, we're going to establish a relationship between the natural reduction factors and an extension, I should say, of the lemma calculus. Because we'll have more than just functions. And we'll see how this works for the conjunctions and implications that we saw this morning, for true or top that we saw this morning, and then we'll extend it to disjunctions. And that gives us already a very simple programming language. And so we'll see how this goes. But you might want to know why is this actually important. Right? So, I mean, Valeria touched on some of these ideas already, but I want to emphasize a couple. Okay, so the first one is that, okay, why is this important? So the first one is that logic is a guide to programming language design. So that means we can understand certain computational behaviors through the lenses of logic. Now we might not have fully understood all the possible programming things we do yet. So we don't have one for every programming feature. We have a logical interpretation, but we're building this kind of relationship, and I think that gives us sort of further insight in how we can understand some of these features and how we can sort of describe them in a more fundamental way. Okay. It is the basis of type theory. And many people these days, many PL people at least these days, are using the proof assistant Rock. Who has used Rock before? Whoa! Oh, okay. Who has used Acta before? All right. Who has used Acta or Coq before? All right. Who has not used any of these two systems before? Great. I love you guys. But yeah, so if you have used Acta or Rock before, well, what's the foundation of these systems? And these systems are built on something called type theory. And as Valeria also already alluded to, type theory is sort of an extension of this propositional logic that I've described, and Andrea will talk about this more tomorrow. But this relationship is really at the heart So I think this is worthwhile understanding. Now, it's also interesting because it gives us a way of proving consistency of the logic. Through I'm just going to call this looking at programs. Okay? And it will become clear what I mean by that as we go along. But the essential idea is, yes, we don't want to be able to prove bottom in our language. And now you might say, well, I didn't even introduce bottom. Okay, so what does this mean for a language to be consistent? Well, consistency maybe in a more general sense means that not every proposition is actually provable. So that should be the case that we can distinguish between some propositions that are true and some propositions that are not true or not provable in our system. And after I've introduced disjunctions, some of you were saying, oh, can't I prove by induction, okay, that a given proposition is true. Okay, so here is a little exercise for those who believe this. Okay. Well, prove that A or B implies A and B somehow by induction, okay, by the end of this class. And I'm loving to see this proved by induction on whatever proposition. Okay. Because obviously this should not be actually the case. So more generally, right, you want to prove that a system is consistent, and that is like if you have this nice relationship, you can actually prove consistency of the natural reduction system by looking at your programs, and you can then formulate a notion of normal forms, which will correspond to normal forms in your proofs, and that will then give you a way of justifying why not every proposition is actually provable, or why not every type is inhabitable. Okay, so what is this Curry-Howard isomorphism? So the idea is actually quite simple. So we will annotate our propositions, A, with a proof term, M. Okay, so this will say M is a proof term corresponding to the proposition A. So in fact, A true, I should say. And we'll have some assumptions. Okay, so this might be under some assumptions. So given some assumptions in the context gamma. Okay. M will be a proof term for this proposition A. So this is a new judgment that we're going to introduce. And we're going to design this by design. Okay. What will happen is that if A is true, if and only if we have a derivation that M is a witness or proof term, so that sometimes you hear that too, proof term or witness, okay, for A. Yeah?
Are those the same kinds of gammas?
Yes, they're the same kinds of gamma. Okay. And as a reminder, what is gamma? Okay, gamma was essentially just a list of assumptions, and okay, I'm a little saying, oh, it's the same. Technically, okay, here we had assumptions A true. I'm going to drop the true here, so there's a little bit of an erasure. There's a tiny erasure. Okay, which I'm going to put a little minus there, which essentially is that I'm going to trope this guy. Okay? But other than that, they have the same structure. And in fact, it will be even more. It's not the case that if you have a proof here, then there will be a run over here, and that proof could be wildly different. Okay? And if you have a proof here, then yeah, there exists some proof over here. We don't know really what the structure of these proofs or their relations would be. No, we're actually going to have the fact that the derivations have identical structures. So we're not just proving that the power of these two proof systems is they're equivalent in some form, but there's really a one-to-one correspondence. And so the way we will see this is, in fact, we will just look at our rules from logic before, okay, and then we'll annotate them with our proof terms. Because I think what is also important is, like, you can certainly think of this as a proof witness, okay? But what our interest in programming languages is that we pick sort of proof terms that are sort of sensible and correspond to some kind of programming idiom. Right? Some kind of programming construct. So I could certainly make up some fancy names for proof witnesses. Okay? So some papers in logic might call them just delta and delta gamma. Okay? Logicians like Greek letters. So delta and, delta gamma, delta implies, delta whatever. Right? That's a proof term. It's called a delta with some kind of fancy subscript. Doesn't mean anything to you, okay? Because it doesn't have a direct correspondence to a programming construct you might be familiar with. So I think part of this Curry-Howard story is that we actually find meaningful programs. So M is a program that has a type A. So the goal is not only just to make up some kind of proof terms, but to also see what are these programs, how do they correspond to programming languages constructs. And by the end, we essentially have a fragment, let's say, of ML or OPL. Okay, so let's get going. Okay, so let's start with conjunctions, because conjunctions are always easy to understand. Okay, so we have introduction and elimination rules. Okay, and so as a reminder, that's what they look like. Okay, so we have A and B, and we're able to prove A and B if we have the proof of A. And we have the proof of B, and I just dropped the true part. Okay. And now I want to give them proof witnesses. Okay. So I'm going to say that M is a proof witness for A. I would love to use a color, but Zina banned me from using a color.
Even purple?
Purple. I will use purple. Okay. And I don't press very hard on it. Okay, so M is the witness for A, and N is the witness for B. So the witness for A and B must incorporate both kinds of information somehow. Okay? And so that is essentially what a pair is. So we're pairing them together. I'm writing pairs with these angle brackets. But you can write them in some other notation, but this is the notation I've picked. And this is indeed our conjunction introduction. And then we have elimination forms. Okay, so we have here A and B. And we're getting out the A. So those are add elimination to the left. And we have A and B. And that getting out the B, and there was our and elimination to the right. So what is a good proof term for this? So for A and B, well, we don't know how we prove this, okay? It doesn't necessarily have to be a pair already, right? It could be some fancy program that would compute some kind of pair, okay? So you shouldn't fix here this notation to be of an exact pair shape, because it could be something more complicated. It could be even just a variable, right? So maybe we proved A and B from just using an assumption here in gamma. So it doesn't have to be a pair. So what we know is it will be some term. Here we know it's going to be some term. And what do we say? How do we give it a term that will give me the first part of the pair? So what is that in the programming language term? First or projection, okay? So I'm going to use first. Okay. And here, if I get the second part out of the pair, that's a second projection. Okay, that sounds very intuitive. Okay, I hope to most of you. Okay, so why is this important? Okay, so well, let's look at local soundness. Okay. So local soundness. What was local soundness saying? It was saying if I introduce a connective, then I was able to eliminate it, and that meant that my connective was not too strong. Okay, so essentially what we argued is we said that we have an A and we have a B. We can form a pair, and then we can get one of these things out. So call it. So this is an AND introduction followed by an AND elimination to the left. So now let's annotate this with our purple proof terms. Okay. So we have here, and then we argued, we argued that we already had a proof of A. Okay. And that proof was sitting right here. This was the proof that we used to justify it. So N was a proof term for A. Okay. So N is the proof term for B. The proof term for A and B, that's the pair of the two things. Okay. And the elimination is that I take the first projection out of this pair. Okay. So what is the witness on this side?
First of the pair.
No. First of the pair is this derivation.
N?
It's just n. Okay, exactly. It's just n. So what does that tell us? Okay, it tells us that there is a reduction. First of n, the pair should reduce to n. That's what the sale says. So local soundness gives us insight into the computational behavior of these terms. It's intimately related to essentially this logical argument that our rules are logically sound. So we can actually justify it. So that's one reading of this. Yeah?
Do we need to get back to the same proof term that we started with? Like, if we got back something other than n, would we still have local soundness? Or would we not have demonstrated it?
So local soundness talks about the types.
Okay.
Okay, so, or the proposition. So we should get the same A. Okay, so we should want to get here we have an A. Put that in a box. And you want to get the same A. That's the same A you want. Okay. So we want to preserve provability. Okay. If we proved an A here, we had a proof of A, we still want to have a proof of A. If I think of types, what just happened is not only that that my reduction rule was falling out of this local soundness rule, but rather it actually says something more. Okay? So I was saying that I can read the A as a type. And this says that I have here a program, okay, that has type A. And it will step to another program that also has type A. Are you with me? Because the reading in here is really important. Right? Logically, I said I had a proof of A, and I did this detour of going from introduction to elimination, and I had already a proof of A, and logically this basically said I didn't gain any information. Okay. Now, from a proof or from a programming point of view, what I say is here I have a program that is of type A, okay, and that will essentially step to a program M that will have the same type A. So, from a programming point of view, this says is that if M has some type A, okay, and okay, one of these reductions. In general, it will step to some other term in prime. Then I will have that this M prime will have the same type, or will be also witness for a proof of A. It will be a different proof, but it is a proof that also is a witness for A. So this theorem, anybody knows what this theorem is called?
Subject reduction.
That's this theorem called subject reduction, okay, or sometimes also called type preservation. And so the subject is M that is being reduced. And if you want to call it type preservation, that's because the type is preserved. So, Wright and Fella in the 90s, I believe, they kind of popularized this idea of proving that a programming language design satisfies type preservation. In fact, they had a separate property that's called progress that then leads to the fact that your language is type safe. But a key part in proving that your language is type safe is exactly this theorem, which is essentially what you get when you do a local soundness argument for your type or your causation. So when you prove this theorem, you would prove it by induction, and typically by induction on the first derivation. By induction on this stepping, sorry. Okay. And then you get one of the cases, which is going to be one of these cases. So, yeah.
So I'm slightly confused because I thought local soundness was a test that we did on connected to check whether it was locally sound.
Yeah.
And like, it looks like first, and like we know intuitively that first of MN is M, but I don't understand why we have the tools to say that. Are we concluding like first of MN must be M if we want local soundness, so we'll define them to reduce to each other?
Yes. So this says that first of the pair of M and N must reduce to M. If we want local soundness.
Okay.
So you can, this is like, basically, if I want to have local soundness, there's no other way I could define this reduction rule.
And do we introduce that reduction rule? Like, what kind of thing is the reduction rule? Is it like, is it a sequence or is it like?
Okay, good question. Okay, so what is the reduction rule? Okay, so reductions is another form of a judgment. It's a relation between two things, two terms. Here this was a judgment about one thing, your proposition. This is a judgment that relates these two things. And yes, setting is another judgment. In fact, again, we said, what is a good judgment? Well, a judgment is one that can be checked. Okay? So I have one way of checking that the program reduces. This is one rule, the rule I've given you. Now we might want to have ways of looking inside. Okay? So you want to definitely think of this as something where I can chain some of the reductions together. Okay? Until basically I cannot reduce anymore. Okay, so think of this as there's no reduction possible. And this is what we then call a normal form. I'm going to define normal forms more precisely, but for now this should intuitively basically. It would mean that you have nowhere in your program something that looks like first of a pair at this point. I don't have to give you any more rules. A different way of looking at this is basically saying this is a one-step reduction, and on top of it we define sort of what is called the reflexive transitive closure of these rules, so you can sort of eventually chain all these things together. Yes?
Previously, A was a proposition which we gave a nice definition for. A now being a type, we haven't yet specified what that is, right?
So far, I've used the same notation. Written like this, but you're certainly getting at the point. Okay, so what is this relationship between types and propositions? So let me put that over here. Propositions, types, programs. So propositions, we have conjunctions, and what's the type for pairs in your favorite programming language? OCaml, programmers to the forefront. Yes. Tuples, so sometimes also called cross products, and often written with this sign here. So this is they call it cross product. Okay. And for the programs, well, you have ways to construct element of this pair, so it will be literally a pair. Okay. And so far we have first of the pair. But we have not only one elimination form, we also have a second elimination form, so that will be second. And we can see that out of the second soundness, our local soundness derivation, right, where we use here and elimination to the right, we will get exactly the second kind of reduction rule we would want, which is essentially saying that I have second of a pair will reduce to n. So it does tell me, yes, if my system is locally sound, I have two local soundness arguments, there are indeed two reduction rules. And if you would essentially have only one of these elimination rules, okay, then you couldn't form this kind of reduction of second of n cross n goes to n, and that would mean your program is essentially stuck because you haven't specified what would happen in this case. So the argument that it is sort of locally sound gives you sort of a different way of looking at it. Yeah?
Is it reasonable to think of reductions as a semantics, or is that something separate?
Is it reasonable to think of reductions as?
A semantics?
A semantics.
Or is that
Yeah, you
something
can think of this as a semantics. Okay. So this is, you can think of this as a dynamic semantics or an operational semantics. So that some people call this an operational semantics. Or dynamic semantics. And some people might call the typing here a static semantics. Okay? It's really just about reasoning sort of conceptually of what programs should, in some sense, do. Or you can think of it as an actual proof. Okay.
Raise your hand higher.
Oh, there's more hand up. Yes.
So in the local settings group up there, is the D and the M on the left-hand side the same as the D and the N on the right-hand side?
Yes. This
Yeah.
D here
Yeah.
does correspond exactly to this D here.
Okay, and the M too.
Huh?
And the M as well.
And M too, yes. This M is exactly this M. That's right. Correct. So that's how it collapses, right? And you can see that, yes, this is a detour in my logical proof. I did like an introduction followed by an elimination. Now, logically, this might have bothered us, okay, because why is somebody so stupid to first introduce an inconjunction and then eliminate it, okay? Now, from a programmer's point of view, you might not be so bothered. Maybe it's still a stupid thing to write, okay, because obviously it can easily reduce to M, okay, but we're more used to this because this will happen during evaluation. Right? So you might be less bothered by this term itself. Hopefully you don't write it in your programs because it's a bit of a stupid program. Okay? But you know, I've seen lots of students write programs. Okay, so that's locus animus. And what's the local completeness before I go on to some of the other connectives? Local completeness is a form of expansion. It's not a form necessarily of reduction. And here we actually reduced also the size of the term, right? So the size of the term or the proof was first of a pair of M and N. Okay? So that's quite a chunk, okay? And we reduced it down to M. Okay? So literally in this reduction step, also the program reduced. Okay? It's not necessarily guaranteed that your program will always reduce in size when you do a reduction step, but here we did. But local completeness is actually the opposite. It's something that doesn't, well, it happens a little bit, you see it in programming languages. You see it much more in type theories. So we start with a conjunction. And we say M is a proof for A and B. And then what did we argue? Okay, so we argued that we can use this proof of A and B to get the A out. And then use this proof A and B to get B out. And then we reintroduced it. Okay. Oh well, now we can reintroduce